It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Biogeotechnics was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on field trials on bio-based ground improvement was delivered by Associate Professor Leon van Paassen at this workshop. Leon van Paassen is Associate Professor at Arizona State University and Senior Investigator at the National Science Foundation Engineering Research Center for Biomediated and Bio-Inspired Geotechnics. He has more than 20 years research experience and expertise in the biological, chemical, and geotechnical characterization of soils in biochemical reactive transport and multi-phase flow in porous media. Past and current research projects include bio-based ground improvement through microbially induced carbonate precipitation, liquefaction mitigation through biogenic desaturation, biomineralization for dust suppression, biomediated ion precipitation for permeability reduction, and mangrove-inspired scour protection for submerged foundation systems. In collaboration with industrial partners, he developed several of these technologies from a proof of concept in the laboratory to field-scale demonstration projects for a variety of geotechnical and geoenvironmental engineering applications. He teaches courses on geotechnical engineering, engineering geology, bio-based geotechnical engineering, and advanced geotechnical testing. Since May 2020, he acts as co-principal investigator for CBBG at ASU and leads the research thrust on environmental protection and restoration, which includes projects on restoring surface crusts of disturbed soil sites, groundwater remediation of chlorinated solvents or heavy metals, nutrient removal from surface water, and the development of microbial-enhanced permeable reactive barriers. His mission is to integrate the fields of environmental biotechnology and geotechnical engineering, aiming to develop sustainable solutions, which improve resource efficiency and reduce the environmental impact of civil and mining engineering industry.
Yeah, so I want to give a talk about field trials we have performed in the past and we have performed in the future, and it's all about bio-based ground improvement. When I talk about bio-based improvement, it's mostly dealing with microorganisms, and what you can see here is that the actual microorganisms are the black dots on the background, which are moving and flickering a little bit. And these larger organisms, actually, they're about 20 microns. They're eating those tiny microorganisms. So we actually have an entire ecosystem at the scale of 100 micron, right? So that is an interesting concept, that if you just take some tap water, particularly from a sewage system, this is what you would see if you put it under the microscope. So if we look at these organisms and what's the concept of bio-based ground improvement? We have been studying that for about 15-20 years now, and the main concept is that you want to achieve some kind of biochemical conversion in the subsurface, and in order to get a chemical reaction running, you can use organisms, bacteria or fungi or other organisms, which catalyze this biochemical conversion, and as a result of that conversion, they change the mechanical properties or the geotechnical properties of the soil. So what we then look at, the products of these conversions are either minerals, they're maybe organic matter, or it may be gas. And each of these products, they will affect the mechanical properties, like they can reduce the permeability or increase the stiffness, or increase the shear strength, or change the volumetric response, making contractive soils dilatant and the other way around. So we can study that all in the lab, but if we want to have this realistically be applied in the field, we have to also do some scale-up studies and try to apply it in the field. So the main challenge is then to get that implemented. So going back to the first process which we started to investigate when I did my PhD, it was all about hydrolysis of urea. So if we take urea and we have a bacteria which contain the enzyme urease, we hydrolyze the conversion of urea to carbonate and ammonium. And then if you mix the urea with calcium chloride, you get calcium carbonate crystals, minerals, and you have ammonium chloride as a byproduct. So these crystals, they sit between the sand grains, and then they can increase the shear strength or can reduce the permeability. So the concept was not developed by me. It was already developed in the early 2000s. And well, in 2003, one of my colleagues at the time, Victoria Whiffin, she graduated and showed that we could cement sand using that process, and she developed some column studies in the lab. And when I started, my job was then to try to scale this up and try to see how fast can we get this into the field. So going from a small lab column, we said, well, the main advantage of such a technique as compared to existing methods would be that everything is dissolved in water. So we should be able to inject it over a long distance. If we can do that, then we have a competitive advantage compared to alternative methods. So the first task was to get a long distance column. So about 2005, we formed one column, and we showed that, yes, we can cement at large distance. But next stage is to scale up is like, well, how do they do that in the field? So in the field, they use injection wells and extraction wells and other kind of pumping systems. So, and in fact, flow is not one-dimensional if you go outside in the field. If you start from a well, it's radial outward, and then if you use injection extraction wells, so that you have different flow geometries. So we started practicing with actual field equipment like perforated PVC pipes to start injecting it, and we showed that we could cement the 1 cubic meter scale. At that time, we found an industrial partner, a contractor, who said, well, if you show us how to do it, then we can implement it on a large scale. So here's a large scale sandbox they implemented. And here we have 3 injection wells on one side and 3 extraction wells on the other side, and several monitoring wells distributed throughout the tank. So we flushed this system first with a batch of bacteria, and consequently we gave it 5 flushes of a cementation solution containing the calcium chloride and urea. And after 12 days, we stopped flushing and we started excavating the sample, and we exhumed this large 40 cubic meters of solidified sand. So that was quite an achievement at that time. And then after, well, we started analyzing, and we found that it's pretty heavily solidified. Some areas we got 25% of calcium carbonate in the sand, but there were also areas there was none. You can see here on the sides, actually, there's no cementation underneath the bottom part of this cemented sandstone body. So within this cemented zone, it was not really homogeneous, still quite heterogeneous. So that was one of the conditions we found. Okay, it's different than other techniques where you're able to more control the strength throughout an improved soil area. But having done this, we started thinking, okay, what could you do with such a process? And actually, we were not the only ones at that time. So this is a nice paper by Adrian Phillips from Montana State University, who lists all kinds of applications, what you could do with urealytic biomineralization, as it was called at that time. We continued to focus on soil stabilization techniques. And actually, we found another industrial partner at the time who had an actual problem in the field. They had to install a pipeline going through a gravel layer. And they said, well, if we install this pipeline with horizontal directional drilling, we may risk that as we drill the hole and we ream the hole, and afterwards you want to pull the pipeline through the hole underneath the river, this borehole could collapse as you start reaming the borehole, particularly if you're in a gravel layer. So they said we need some countermeasure to try to cement the gravel so that when we drill a hole through it, it will not collapse. And we did some trial and error, optimizing the recipe there. And then we gave it a 9-flush treatment procedure. We were able to cement the gravel container and then drill through the container and found that the hull was stable. So this was sufficient for the client, who was actually paying for the entire project, to increase the budget to take this risk mitigating measure and to prevent the borehole collapse. So still we needed to optimize because the nine flushes is far too expensive. So we had to reduce down the recipe and do some trial tests in the lab. So here we built a direct shear test device where we could shear well, limited number of flushes to see when we would see some effect of the biocementation. And here you can see that the calcium carbonate is really distributed throughout the gravel, not really cementing all the grains. But we found that even after 2 flushes, you would already see an effect. And this was not really heavily cemented. So if you would shear it, or if you would open the box, it would still collapse completely. But it still showed an increase in shear stress during shearing, which was then mostly related to increased dilatancy, because some bonds are remaining intact as you shear the sample. And as a result of that, you get increased dilatancy because the larger aggregate lumps of grains need to pass each other. So there was an increase in the dilatant performance, and that was enough. So we decided that 2 flushes would be enough to take away the risk when you are drilling through a gravel layer. So once we redefined the recipe, you start ordering equipment and chemicals, so urea and calcium. If you scale it up at the field scale, you see that it actually is large containers with liquids. These are then mixed using a large scale mixer and then transferred through pumps and distributing, flow distributors, going through the injection wells, which are then localized here at the center with extraction wells along the side. So in total, I think we treated 2 times this volume, which is about 800 cubic meters of sand and gravel. So consequently, we treated the sample, and we found it was pretty hard actually to monitor what would happen. At some locations, it was 4 to 20 meters below surface. And how do you prove that you actually have a strengthened soil in that site? So we pushed some CPTs, but yeah, doing CPTs in gravel is not ideal. You get a lot of high resistance values, and you don't know whether your high resistance is actually due to hitting a large gravel particle or whether you're hitting a cemented area. So we could not see any significant difference between the treatment zone and the non-treatment zone. We found one monitoring methods, which was electrical resistivity survey, which could be used to indicate the zone of treatment. So this would indicate that we actually injected a saline solution, and well, we can see the injected area is constrained, and that gives us some idea about where our the area of our treatment zone. But it was very difficult to actually get a proof of how much cementation and how much strengthening did actually occur. At the shallower depths, we could extract some samples, and there we could find that there was some calcium carbonate on the sample. Whether this was because we treated it or whether it was already in situ, that's another question you need to think about when you are going to monitor what's your background value and how variable is your background in order to prove that you have done a decent job. So at the end, this is the installation of the pipeline going through the borehole, and it came out at the other end. So contractor was really happy, and they said we did a successful job. However, well, as a scientist, we said, well, where's the evidence that we actually, because of the biostimulation, this is why it worked. So we were not fully satisfied, but still we would say, yes, we proved that we can stabilize both gravel and sand. We developed all kinds of injection, mixing, and monitoring methods and sampling methods. We established several empirical correlations between the amount of calcite and the strength. And we came up with many possible applications. However, the large-scale application also showed that we still have this limited evidence, limited control of the process and homogeneity of the soil or of the treatment. That's still an issue. And actually it was quite expensive. Even the 2 flushes strategy, we came up with a number based on the overall budget which the contractor had to spend, which was about $400 per cubic meter of treated soil. And then where are these costs? It's about 25% is in the urea and the calcium, 25% in the removal of the ammonium chloride. Otherwise you end up with a well, heavily fertilized saline soil, and that's not good. And then another part was the cultivation of bacteria, because at some stage, if you do bioaugmentation, you need so many bacteria that we could not grow that ourselves as geotechnical engineers. So we hired for an industrial fermenting business. So a company specialized in cultivating bacteria. So we had to buy them, and then they were quite expensive. The other part is the environmental impact. Many people who write papers on this topic, they always say this is an environmentally friendly process. Well, actually, the impact, it really depends on how much substrates you're using. And also urea and calcium chloride are resources, and they're not necessarily environmentally friendly. So there is definitely some environmental impact related to this process. So as a result of that, we said, well, we need to move forward. So we can optimize the process, trying to see if we maybe can use less resources, use other applications where lower strengths are required, use other processes to do carbonate precipitation, or use alternative products like the biogas or the biofilms. So in terms of other applications, one of the main applications where people are looking at right now is liquefaction mitigation, but also dust suppression and erosion control, because, well, it's suggested for liquefaction mitigation, you only need to cement for a very low amount. And for dust suppression, you, for example, you have only a very thin crust. So those are relatively low volumes over large surface areas. So there may be potential, and that is why several research projects focus on some of these applications. Also, if it's not a constructural element, then a low strength or limited homogeneity may not be an issue in that case. For many of these applications, after that, many field trials have been performed. So they have performed a liquefaction resistance increase under a dam in Washington. And well, for environmental applications like the immobilization of metal contaminants, there's a field trial which has been performed. Some colleagues in France, they did some slope stabilization, and also we did some new project here in Canada for some slope stabilization. And then, well, wind erosion mitigation, fracture sealing, and beach erosion mitigation, all projects have been investigated using this MICP by urea hydrolysis. But we also try to say, okay, what if we use another process? So looking at the urea-based process, in fact, you need some resources and you need some microbes to generate your cemented sand, but you also have your ammonium chloride, which is a waste product and you need to treat. So what do you do with that? This is a significant impact both on cost and environmental impact. So then we looked at alternative processes. So for example, denitrification, it also uses resources to produce the cemented sand. But in this process, the substrates, which are calcium fatty acids and the calcium nitrate, they're actually food sources for the microbes which already live in the ground. So we can do biostimulation instead of bioaugmentation. And then the only byproduct of this process is nitrogen gas and maybe some carbon dioxide. And the bacteria itself. So both these products are, well, have less of an environmental impact than ammonium chloride. So that may be beneficial. And actually we did some investigations, and we were able to cement some sand. We did a 2-meter length column. We used some garden soil just to grow the denitrifying microbes. And we showed that we could do this simultaneous formation of biomass crystals and gas on these fatty acids, but also on sugars, we get about 9% calcium carbonate at the start of the column, but eventually we got lower and lower amounts, less than 1%. And we needed 100 days to get this average of 3% spread throughout the column. And so again, we had very heterogeneous treatment, and it was pretty slow as compared to the urea hydrolysis. It also required maybe 20 or 30 pore volumes to be flushed through the sand column to get to that level of strengthening. Potential benefit we investigated was that both the resources we use for this process can be derived from waste streams. For example, the calcium nitrate can be derived from an ammonium-rich waste stream. Oxidizing the ammonium results in nitrate, and it also results in acidification. So to buffer the pH, if you use a lime for that, then the lime gets in solution and your end product will be calcium nitrate. So that is one way to get a cheap source of substrate. And the other one would be the calcium fatty acids, maybe derived from organic waste streams, which are fermented and then results in calcium fatty acids. So combining these two and put them in the ground would then result in improved sustainability. Obviously, this depends because you have to have available waste streams in your area and not have to transport them over large distances. Otherwise, this process doesn't become very sustainable again. Another issue related to the denitrification process is that the nitrate reduction is in fact a multi-step process. So nitrate is converted to nitrite, and nitrite to nitric oxide, and nitric oxide to nitrous oxide to get to nitrogen gas. There's different enzymes involved to do all these steps. And if you get accumulation of one of these two compounds, then these enzymes may be inhibited and you get accumulation of these compounds, where the first two are toxic and the last one is actually a very strong greenhouse gas, even stronger than methane. So you don't want this product to be an intermediate product. So you have to do something on your treatment strategy to try to prevent that from happening. So, but we tried, and one of the methods to avoid this accumulation of intermediate compounds would be to use relatively low concentrations. So in the first test, we got high cement contents, but we were not able to get a strength measurement. So we repeated that experiment, but now did it under triaxial test conditions. Gave it 15 flushes of a 10 millimolar concentration solution of calcium nitrate and 12 millimolar calcium acetate, mixing this and flushing a sample 15 times in 35 days. We got about 0.7% of calcite on average within the sample. And because we did it inside a triaxial cell, we were also able to measure the increase in stiffness and the increase in strength at lower strains. So some mechanical improvement and overall a bit more homogeneous distribution of our cementation strength. Disadvantage of this, another disadvantage of the process is that as we're treating the sample multiple times, and we have to give it multiple flushes because we want to keep the concentration low enough in order to avoid this accumulation of inhibiting compounds. After multiple flushes, we see that because of the entrapment of the minerals, but also the byproducts, the gas and the biomass, we see that there's significant clogging happening in this sandy soil. And so that also affects the homogeneity of the treatment process. And here we saw that actually after 4 cycles or after 7 cycles, that the permeability is significantly reduced due to the entrapment of the combined biomass, biominerals, and biogas. Another feature of the byproducts, which is the gas in this case, is that the gas actually may destabilize the soil, and particularly under low confinement pressure, we see that the gas accumulates and loosens up the soil, which actually counteracts the strengthening effect of the biocementation process. So based on these processes, we felt like, okay, maybe this MRCP by denitrification will not really work in the field. So let's look at some other products. So at that time, we found in literature, there were some studies on using desaturation of soils for liquefaction mitigation. The concept is that if you desaturate a soil, you fill up the pores with compressible gas, and as you're shaking this ground or you're shearing it, it's because the gas is compressible, you will not build up so much pore pressure, and as a result, if the pore pressure is not building up during cyclic loading, you would not see that if the pore pressure goes up, the effective stress goes down until it fully liquefies. So you could mitigate liquefaction triggering from happening by getting some entrapped gas in those pores. And actually we said it's similar like an airbag. Yeah, you take up the hit from the earthquake as these gases is compressible. So that concept was demonstrated already in 2010 or 2011, and also by Dr. Hay and Professor Chu in Singapore. They did some shake table testing and demonstrated that you only need about 5% reduction in degree of saturation to significantly dampen those pore pressures during shaking. And actually, if they were lowered it to 20% desaturation, there was almost no increase in pore pressure during the cyclic shaking in a shaking table. So that looked pretty promising. Particularly if you then do the calculations on how much actually substrates do you need. So we did some strengthening tests with MICP by denitrification, which showed that we need 1 to 3% of calcite to get some, measurable strength. This would mean about 25 to 70 kilograms of substrates per cubic meter of treated soil, or 3 to 10 flushes. If we compare that to denitrification for liquefaction mitigation, we only need about 20% nitrogen gas using the same recipe, which would be only 0.7 to 1.5 kilogram of substrate per cube, which we can deliver in one flush. So the number of flushes, which means time of treatment, and the amount of resources required is significantly lower, about 40 times less for desaturation as compared to precipitation. So that seemed like a viable solution, but then we one that's okay, how do we prove that? We have to do some field scale trials again, and we have to demonstrate that we can actually get the gas in there and that it's how it's distributed in that field. Second question we need to answer, is this desaturation actually persistent? Do these bubbles, do they easily escape from the ground? So those are two questions we still needed to investigate. And for that, we tried to do a field scale test. So a few years ago, we teamed up with our colleagues from Portland State University, Arash Ghosh Ravifar and Diane Mook. They got a grant from NSF to do a field study in Portland. And Portland is actually one of those cities on the west coast of the United States, which has potential risk of liquefaction in case of a heavy earthquake, and this heavy earthquake is actually about to happen. You never know when it happens, but it's expected that in the near future, maybe 5, maybe 10, maybe 100 years, there will be maybe a magnitude 8 or magnitude 9 earthquake on that part of the west coast of the US. And if that happens, what they did analyze that all these areas which are lined as purple or pink, they have a very high risk of liquefaction. So, and when that happens, there's also a serious consequence, because on this area here is very close to the international airport, and on the other side, along this west side of the Willamette River, there's a lot of energy storage, like large oil tanks. So if this would all liquefy in those oil tanks, which have been built before the actual design codes on earthquake construction were in place, the soils would liquefy, and the entire energy storage for the state of Oregon would actually slide into the river, which is a huge environmental but also logistical catastrophe. So there was quite some emphasis and some some societal need to do something about that. So we tried 2 test sites, one close to the airport and one close to the energy storage site, where we did some field trial. And this is a bit the layout of the field trial, where we had a single injection well in the center, surrounded by 4 extraction wells. And we've learned in a way to a little bit optimize if you compare this footprint with the original footprint we did in our first field trial 10 years earlier. Here, the extraction pumps are operated by a car battery, and the injection pump and storage containers are much smaller in terms of footprint than in the first field trials. So at the site, we did a lot of monitoring. So we have a monitoring well where we have sensors installed. It's called Teros 12 sensors. They measure salinity and water content in the subsurface on a vertical array. And we have some cross-hole sensor arrays where we measure pressure wave and shear wave velocities as during and after treatment. So the treatment involved injecting substrate solutions. I think we used 25 millimolar calcium acetate, calcium nitrate solution, up to 14,000 gallons, which was about 60% of the total pore volume injected within that area. And as we injected it, we measured the salinity of the injected liquids and we measured the salinity of the extracted liquids. And based on the difference, we could then state something about how much of the injected substrates would have been converted. And we could make an estimate of how much substrates would have been consumed. So here's the results from that array of sensors, which was placed in the middle between injection and extraction wells. And we could see that this was the initial saturation ratio, or the volumetric water content divided by the initial volumetric water content. And at the time as we started treatment, which was around September 9th, 2019, we saw that there was an immediate significant reduction in this degree of saturation. So which indicated that actually the gas was being formed and the gas was being trapped in the subsurface. At the same time, you can see here a peak of salinity. Typically, this would indicate that some of these substrates are actually bypassing the sensor, and after it has passed, it reduces again, which means that there's some consumption of these salts. There's still some residual salt here remaining, which may indicate some leftover substrate solutions, or maybe due to the injection of these salt solutions, we have mobilized some other salts in the ground, which may not be consumed in the end. So looking at the cross-hole pressure wave and shear wave measurements, we saw that the pressure measurements were going down during the treatment period, and after the treatment period they remained low, which means that the pressure wave velocity is actually directly correlated to the degree of saturation, and a reduction in pressure wave velocity just means that you have desaturated the soil at least to a 95% degree of saturation. So as we speak right now, so these are the measurements up to 2019. We have been continuing monitoring these sites, and we have seen actually that even at today, the pressure wave velocities are still around this 300-400 meters per second, which still indicates that the soils are desaturated. So we have at this moment we have proven that there's at least a 3-year durability, a 3-year persistence of the entrapped gas phase. Shear wave velocity measurements indicated there was actually no significant effect on the shear wave velocity, which means that the biocementation of a single flush doesn't have a significant effect on the strengthening, as the shear wave velocity is directly correlated to the amount of strengthening in the ground due to biocementation. In this profile, you can see that the desaturation or the reduction in pressure wave velocity happened at all different heights of the treatment area. What you can see here is actually at the site after treatment, we mobilized one of the larger facilities from the National Science Foundation, which is the T-Rex shaker machine. We installed a lot of sensors in the area to monitor pore pressure response and acceleration as a result of induced shaking. And this machine can then induce significant shaking, which, well, maybe not a magnitude 9 earthquake, but at least significant shaking. We found, well, the results are still being investigated. They were not fully conclusive. We still saw some pore pressure buildup in the area, and we have to try to find out what's the cause of that pore pressure buildup. So we're still investigating that data at this moment. Based on the field trial, again, we could make a cost estimate. What would it cost to apply this in a real application? And we compared it with a permeation grouting technique. So the base case was we have an existing facility standing on a liquefiable soil. If it's already existing, you actually cannot access it using jet grouting or deep soil mixing. So, but we could inject it using either permeation grouting with a very low viscosity grout, or using diagonal wells, so we can actually access the soil underneath the structure. As an alternative, if the desaturation would be persistent, and we've proven that we can actually inject over distance of 3 to 10 meters. And so then we can calculate how much materials do you actually need to treat that specific area and get the same liquefaction resistance as compared to using microfine cement. And you can see mainly in the material cost, there's significant reduction and economic value related to that. So in conclusion, I think we've proven that well, microbial-induced carbonate precipitation and desaturation and precipitation. So the second here is what we refer to when we use denitrification, because we desaturate and precipitate simultaneously, or just the desaturation phase. They all can be used to stabilize soils. Precipitation is possible. Particularly with denitrification, it requires more time and more flushes than just desaturation. But still, the heterogeneity and quality assessment in the field are an issue. And so we have to come up with, well, new methods or good methods to prove that it actually works. Regarding the denitrification, the clogging in the biogas of biogas and biomass may affect the delivery of the substrate. So that compared to urea hydrolysis, that's a main disadvantage. But if we can rely on desaturation as a viable stabilization technique, then it's much cheaper than precipitation. But it has a much lower durability. So at this time, we have proven at least a year, or actually 3 years, we have already proven the durability of the gas phase in the ground. So that's a good thing. But we're still continue to monitor this and demonstrate the durability. We're still planning to develop test and monitoring methods, both for the desaturation, but also for the cementation. We need to develop more and new methods. And we're still developing numerical models, which can be used to predict the substrate and product distribution and use for treatment design. And so those are things we're currently still working on. Another feature what we're working on was one of the questions we got when we applied this in the field is then how can you prove where the gas is? What's the gas distribution? And how is this affected by the heterogeneity of the soil subsurface? So we know that soils are heterogeneous, but then how does it affect the formation of the gas and the distribution of the gas? And then once you know where the gas is in a heterogeneous soil, what's the effect of an heterogeneous distribution on liquefaction resistance? So all these questions still need to be answered before we think we can actually go and commercialize these kind of technologies. So an idea about the studies we're currently doing to assess that effect of heterogeneity in the subsurface is these relatively large scale screen test. So this is a 1 by 1 meter screen, 5 centimeters wide. We fill it up with different sand types. So we have a coarse grain sand and a fine grain sand, and we can see that the differences in grain size have resulted in differences of hydraulic conductivity, at least the initial hydraulic conductivity. And as a result, we see that the flow velocity in the coarser grain sands is much higher than in the fine grain sands. So this was just a flush with water, and we added some food dye to visualize those flow velocities. But if we now look at the substrate injection, we see actually that these are substrate solutions containing 25 millimolar of salt, and they already show that they're, particularly in the coarser grain sands, there's a significant gravity component in the treatment solution. So the salt solution is slightly more dense than the surrounding groundwater in a freshwater environment, and as a result, you may get some gravity-driven flow, which actually may be a good thing because it also distributes them vertically those substrate solution through the finer grain sand. So you get further distribution of your substrate solution than you would get if you would just use water. And actually, we could continue to monitor to also visualize the distribution of the products. I think that's it. So I have plenty of time for questions, if there are any. Yes, I think that is one of the suggested methods. Particularly the shear wave velocity is a good way to measure increased strength and stiffness. We haven't done that in the past, but I know that currently my colleagues at UC Davis, they are preparing a field trial in which they have different cross-hole types of shear wave velocity measurement. It's both cross-hole or it can be down-hole from a CPT truck, right? So we have nowadays seismic CPT trucks, which they can measure the shear wave velocity along when they push in the cones. However, there's a small caveat, is that your contrast needs to be significantly large, right? So that's always where we want to optimize the lowest amount of cement required, but if it's too low, we're not able to detect it. So it may be there, but there's not enough contrast to see the increase in shear wave velocity, and that's in the field with a lot of heterogeneity. That's a bit difficult. Yeah, so you really have to do a baseline investigation, and then you have to do like progressive monitoring during treatment. So that is possible. But yeah, my experience so far, we have not been so successful in field monitoring, particularly also because often there's not very limited budget for continuous monitoring. So yes, if you team up with a university and use free student labor, then maybe. But in commercial projects, that's yeah, it's
very difficult.
My experience is that the budget for monitoring was very limited. Yeah, so well, I always have discussions with my colleagues at ASU on this topic because Edward Kavzanjan, the director of the CBBG, he did a lot of research on the EICP as well. For me, EICP is the same as MICP from urea hydrolysis because it just uses a different source of enzyme. There are slight differences, which means that the enzyme extracted from the jack bean or soybean may have, well, it's a different type of biomass. So if you mix this in the ground, there will be different adsorption of the biomass to the host sand where you want to cement it. And then there's also, there's different strategies. If you can mix the enzyme before you inject everything and mix it all together with the calcium and the urea, or you can inject it sequentially. But then using the jack bean, I haven't seen people doing that sequentially because they feel that they lose the enzyme as it doesn't adsorb that well as the bacteria. But these are, well, you cannot generalize that. So in fact, you have to do a sort of a pre-feasibility study on a soil from the site to see what your optimized treatment procedure must be. And then you can use EICP just as well as MICP. And at the CBBG, we've done some larger scale columns with EICP. But my experience was there that we used a crude extraction method on jack beans, but we found that the extracted enzyme was still quite large relatively, or easily absorbing to the sand. So we could use it in relatively coarse sands. But if we went for finer sands, we saw a lot of filtration of the enzyme at the injection well. Yeah, so that's and the injection pressure is typically that is a good parameter to take into account. So as a general rule of thumb, I say it should never be higher than your overburden pressure, otherwise you get fracking. So if you have too high injection pressures, the liquid wants to go somewhere, and you just start lifting up the ground, or around your injection well, you get a vertical crack, and then all your liquids appear up at surface, and you don't really inject into the formation. In some cases, if you would like have a clay layer on top of a sand layer, then you can apply some higher injection pressures. You make it, and in some cases, you may actually use the fracking to get your substrates at a larger distance. Yeah, you have to engineer your injection pressure in such a way and then you can play with the flow velocity versus the reaction rate to optimize the distance of treatment. So if you're limited by a limited injection pressure that you can only have a flow velocity of 1 meter per day, then your reaction rate should be slower, so you can get a larger injection distance. Yeah. So going for the extracted enzyme from the soybean, I think you can save a significant amount of cost in terms of the bacteria we use in the first application. On the other hand, people are now using biostimulation in some cases, so they can use in situ growing urolytic bacteria by having a specific stimulation solution. That requires a lot of flushes, right? Not necessarily more substrates, but it requires a lot of flushes to get these active urolytic bacteria in the ground. But you may have more homogeneous cementation results than using bioaugmentation with either microbial urease or soybean urease. And the other way to optimize, that is also something they found not so recently, but a few years ago, with the EICP, they added a milk protein.
Yes, yeah.
And by adding the milk, they saw that the crystals, there were less number of crystals, but they were larger, and they were sitting more at the contact points, which showed that they had much more efficient precipitation, and then you need less resources. So I think with the innovations done in the recent years, we can lower that number from $400 per cubic meter to maybe to 100, right? But still it requires resources. So it's not that you get it for free. Yeah. So we saw fracturing, particularly in shallow depth, right? So if you're shallow, you have less overburden pressure. So even you can actually lift up the entire surface by trapping nitrogen gas if it's too much. But if we're deep enough that there's significant overburden pressure, and we do not form too much gas, then we have seen that this. So we've done some denitrification test within a triaxial test setup. And there we found that we don't see any fracturing. So we see that the gas are just filling the pores and just staying in there without any crack formation. So you can suppress the cracking by working at larger depths. Yeah. So with the denitrification, it is a complex process, but in terms of engineering, it's actually pretty simple. because you just mix two substrates and you pump it in the ground, right? So it doesn't require multiple phases. It doesn't require too much mixing of bacteria or enzymes or growing enzymes or buying enzymes. It's just two chemicals. One is a fertilizer. One is vinegar and calcium carbonate. So that's relatively simple, but then it's complex in terms of there's a lot of interaction between the different phases. So that makes it complex. Yeah, so the two strategies, three, okay. One is adding a little bit of plant fertilizer, which contains like the nutrient elements like iron, sulfur, phosphate. So any bacterial growth needs those elements. So you need to add a little bit if you don't want to rely on what's already there. So if the bacteria get out of these micronutrients like iron and sulfur, they stop growing, and then your reaction may stop. So second is that I always overdose a little bit the acetate, because if you have more acetate than there's nitrate, then your nitrate is consumed and the acetate is less severe or less harmful. Or optimize it in such a way. So we found that the maximum growth ratio of acetate to nitrate is 1.2 to 1, but they never grow at the maximum growth rate. So a 1-to-1 ratio is more easy for engineers to remember, but also it is working pretty good in consuming all the substrates. We do see that it does work in seawater, although you have a bit competition with sulfate reducing bacteria, because the seawater contains sulfate as well. So we may add a little bit more acetate. Otherwise, the sulfate reducing bacteria are taking up all the acetate, and you end up with some nitrate left over. But yeah, as long as the nitrate is present and there's sufficient organic substrate, then the denitrification works. One thing with the seawater condition, we analyzed theoretically, but not yet practically demonstrated, is that the byproduct of sulfate reduction is hydrogen sulfide. So this may be toxic, or it may not be desired byproduct. But then again, the hydrogen sulfide may then again react with available anaerobic iron. So there's a lot of, it becomes a bit even more complex chemistry. So, but we have to do those tests to see if the gas is still stable, and what are the residual byproducts of that complex environmental condition. I use it in my class as well as just design a field trial, and that can be for an environmental remediation project. And it's just thinking about, okay, what are the potential chemical reactions taking place? But you have to install wells, and you have to do a Darcy flow like calculation. You can make it more complex, making it anaerobically, or partly in the Verdose zones. You have unsaturated flow. So yeah, I use it a lot in my teaching as well, as an example. Yeah, definitely we've seen that we targeted a certain area, but we found particularly the nitrogen gas much further than we actually intended. So the gas is spreading, the bacteria may spread as well, although bacteria like to absorb to the sand grains, so they are not easily flowing out that much.